The next paper is called Adversarial Attacks and Oblivious Recommender, presented by Konstantina, Christakopoulou.
Hello everyone. I'm very happy to be here to present to you the last work of my PhD before I joined Google. It's the joint work with my advisor, Professor Arindam, Banerjee, and the title of the talk is Adversarial Attacks and Oblivious Recommender. So first of all, why care about the problem? So essentially we all know the recommender systems are such an integral part of our everyday life. However, we also see these many real-life examples where they're exposed to a variety of threats from adversarial parties. Like, for example, there are fake user profiles which are being generated in order to promote their views about their own political ideology, or for example, there are these fake product reviews which are trying to bias people's opinions favorably or against certain products. So it is really important in order to make safe artificial intelligence and safe recommendation systems to make sure that they are robust against such attacks. So the question that we're interested in this paper is, before being able to build such robust recommendation systems, we want to be able to understand how vulnerable existing recommendation systems are to adversarial attacks, and in specific to attacks which are generated by machine learning themselves. So first of all, what do I mean when I say adversarial attack in the context of recommendation system? Normally, the way we represent the real recommendation system data would be have this interaction matrix or rating matrix of real user with items. Now, in the context of an adversarial attack, you have this extra small budget of fake user profiles, which are rating a couple of items with a specific intent. So there have been lines of work in this area, and in fact, this has been a large literature in shilling attacks and recommender systems, where the idea is that these adversarial user profiles essentially have this high rating, for example, in this specific target item that they want to promote, and then they have some other ratings which are, for example, normally distributed in a couple of other items just to make sure that they are undetectable. Of course, there is much more literature, but I'm giving you just an example. Now, one limitation of this kind of work is that it has mainly focused on hand engineering these fake user profiles. Now, there has been this other line of work in machine learning, which is the one of adversarial examples, where the idea, which is especially focused in image classification domains, is that you have this image, let's say this image of a school bus, and then you want to find what is the minimal perturbation vector that you want to add to that image, so that with high probability, some oblivious classifier is going to misclassify it to be something else, like, for example, to be an ostrich. So now, this is where our work comes in, and what we're saying is that essentially we want to combine these two lines of work. And what we want to do is that we want to revisit this concept of shilling attacks and recommendation systems, but from a machine learning optimization perspective. So when we want to deal with this problem, however, we need to consider what makes a recommendation setting different from, let's say, the image classification setting. So first of all, we need to consider that we have this collaborative filtering principle. And so it is not clear whether this is making the recommendation systems more robust against such attacks, or maybe it is going to lead to more cascading effects because of this interdependency among users and items. The second is the fact that we're not sure what undetectability of attacks would be in this case. For example, in image classification, it suggests that you don't want it to be noticeable by the human eye. Here we need to redefine what that means. Now, the third part is the fact that by definition these attacks are poisoning attacks, meaning that essentially every time some adversary decides to input this fake user profile into the data, the recommender system needs to be iteratively updated. And the fourth challenge is the fact that we do not have access, the adversary does not have access to the gradient of the recommendation system. And this is in contrast to most work in adversarial examples where they assume that they have access to the gradient of the oblivious classifier. So now, having these different challenges in our mind, let's try to formulate this problem of how can an adversary try to manipulate and attack an oblivious recommendation system. So essentially, we formulate this problem as a minimax game between two players. The one player is the oblivious recommender system, and the other is the adversary, and each one has its own set of parameters and its own objective. And then there is a duplicated game, general sum form going on. So let's see what are our assumptions. The assumptions for the recommender is that it is oblivious to the second order. It doesn't even know that the adversary exists. And the assumptions for the adversary is that it can actually evaluate every time that it inputs some fake user profile, it can see how the predicted scores from the recommender are going to change. So let's see just a rough example. Essentially, the idea is that in the very beginning, the recommender system says that I want to fit the model on my data, so I have my own objective, and I'm going to essentially learn my parameters. Now, the adversary comes in and it says, I want to create this fake user matrix set, which is these fake user profiles, and then these fake user profiles are going to be injected into the data of the recommender system, which is going to say again, I'm going to fit the model on my data, where now the data is both fake and real. And so then, this iterative procedure is going to continue up until the adversary says that I want to optimize my goal. So let's see what is the goal of the adversary. It's a twofold goal. The one goal is that it wants to make sure that these users are indistinguishable from real users, because it doesn't want to be noticed. And the second goal is that it wants to capture some adversarial intent. So for the very first goal of unnoticeability, what it really means is that we want to make sure that these adversarial users are distribution preserving, meaning that for each specific item, if you look at the distribution of real users and the distributions of fake users, how they have interacted with it, you want to make sure that the two distributions are close to each other by some distance metric, like for example, just standard divergence. So then if you think about that, in reality, the generative adversarial networks framework is a great fit for that, because it's exactly what it's doing. And so then this becomes the very first stage of our attacker strategy, where you're feeding generative adversarial networks in order to learn this initial fake user profile matrix. Now, however, the second goal, which is the main goal of the adversary, is that it wants to optimize its adversarial intent subject to the constraint of unnoticeability. So this f sub a function, this is the one that captures the adversarial intent, which could be anything from targeting a single user item pair, or for example, for targeting a group of users or a group of items, and so on. So every time you see such an objective, you're like, great, let's do gradient descent, and in fact, projected gradient descent because you have this constraint. However, as I mentioned before, the challenge is that we don't have access to the gradient, and so because there is this iterative procedure going on. And so essentially what we do here in order to overcome this challenge is that we're saying, given the fact that the adversary has the opportunity to evaluate the recommender's function on different kind of fake user matrices, essentially we can use k different directions, k different z submatrices, in order to be able to compute some approximation of the gradient. And so using that then, you can do your projected gradient descent for this approximation. So now let's look at some results. The results that I'm focusing on here, although the formulation is general for any kind of recommender, these results are focused on the low-rank recommender model, and they are shown in the Oblivious dataset. So here, first of all, the first kind of attack we looked at is targeting a single user item pair. And so what we looked at here is the fact that on the x-axis you have the z-STD iterations, and the y-axis you have this run clause, where it's 1 when it exists in the top list of this item exists in the top list of a user, or 0 when it does not. So what you see here is that on the 16th z-STD iteration, you managed actually to remove that item from the very top one recommendation list of the user, and then top 5, and then top 10. So this is a successful kind of attack. Now, however, if you look at another kind of attack, which is that you want to target the average score of an item over all users who have not rated that item, we see that this is a hard task. Specifically, what I'm plotting here is what is the difference between the predicted score for that specific item and user before the attack minus after the attack. Ideally, you want that number to be large and to be positive from the side of the adversary. However, you see that every user follows their own trend. And so then, however, we realized that if we were to think of like an adversary, what an adversary really wants to do wouldn't be to just target the average score of an item, but instead they will want to target this average score of the item, but only over the users who would have liked this item. So then we realized that a type of attack that the adversary could do would be to actually say that I want to target the top user of the item, meaning the user who would have been predicting the item had the attack not happened. And so then when we do that, and what we're plotting here is what is the effect, the average, this average attack difference over all the top K users. And what we see is, for example, if you look at the top 10 users, then their delta, their average delta, is going to be high, like for example 8 when you see this y-axis. And so we can see this cascading effect, which is essentially that even despite the fact that we target a single user item pair, we have this cascading effect where we essentially target a group of users or a group of items. And so just to conclude, what I talked about here is this general framework of how to produce this machine learned adversarial attacks for a recommendation system. And I described a little bit our algorithm about how can we leverage this zero-order optimization technique. And we considered a lot of different kinds of attacks. I just went through a couple of them, but in the paper you can find group attacks, or even, for example, when you do an attack with a good intention, like for example, improved modeling of a group, or fair modeling across two groups. What I think is the main takeaway from this talk, what I would like to take, would be that we saw that there is this vulnerability, at least with low-rank recommender models, to this kind of attacks. So I think it's a great opportunity to do more work in the area of defending recommendation systems against such attacks. Thank you very much.
Questions?
Thanks for the next talk. So, how does your framework in this type of attacks compare to other scheme attacks like power user attacks or average attacks? Can you put them in the same scale? I mean, are they comparable, or is this something fundamentally new and incommensurable as a form of attack?
Thank you for the question. So, as I said before, and as you mentioned, there has been a lot of literature on this kind of hand engineering attacks where, for example, this average kind of rating would be one such attack. It's not really hand engineering, but it's a very specific part. We haven't compared in this work with any other kind of shilling attacks, but I definitely think there is more room there. What I believe for this specific framework is that it could capture a large range of adversarial intents, just because of the fact that we do not allow to the adversary to have access to the gradient, and we do this essentially zero-order optimization. This allows us to basically optimize this wide variety of complex adversarial intents that I believe it would be unfair to compare to when, for example, you did some average attack for another kind of intent, which is not as general. So maybe if we're targeting a single user item here, I think there is room for comparison. But then for the more complex kind of intents, I'm not sure how exactly you compare.
More questions? Where are you? Is there a question? There's a question back there.
Hi. Thank you for the presentation. I wonder how your system would react to maybe there are users in the system that are not not following the general trend, and maybe it's their real behavior in the system. So actually, do you have anything that can distinguish the real users from the intentionally harmful users?
Thank you for the question. So essentially, if you remember, we have this very first part, which is the unnoticeability goal that the adversary has. And so we have this notion of making sure that the distribution between the real users and the fake users is close to each other. And so even though I didn't show in the results here, we actually measure every time we're doing this repeated game, we're measuring this total variation distance or other kind of metrics of distances between the two distributions, and we see that they are unnoticeable. Now, this is from the side of the adversary. From the side of the recommender, we, as I said, it's not an adversary-aware system, so there is no such detector module for trying to detect this kind of adversarial users.
Good.
Thank you very much for the talk. So it's very
Can't hear you.
Yeah, it's very interesting talk. I have a small question. Do you have a comment on what types of recommended systems is more susceptible to this type of attack? And I mean, along the dimensions of the type of learning models, the frequency that they update their model, and other dimensions.
That's a great question. So the experiments have actually focused only on the low-rank recommendation model setting. So I do believe there is like a huge area of work that needs to happen for other kind of models. My intuition, what it tells me, is that the kind of models that have more randomness inside, and so there is some probabilistic notion where essentially you're doing some sort of explore-exploit, potentially would be more robust to adversarial attacks. I haven't really explored from the modeling part, let's say, if deeper architectures are going to be more or less robust, so I think there is definitely scope for that to happen.
Your questions? Okay, thank you very much.